Hey, let me ask you something. Did you know the Earth is at the center of the universe? I'm just kidding. But these dummies did until the 16th century when Renaissance man Nicholas Copernicus introduced the heliocentric model, which said, hey, contrary to popular belief, the sun is at the center of our solar system, not the Earth. Now, Aristarchus of Samos, a Greek astronomer, may have figured this out like 1700 years earlier, but hey, who's counting, huh? Aristarchus's and Copernicus's ideas have given rise to the Copernican Principle, which, in a nutshell, says the Earth ain't nothing special. A lot of people weren't too happy to learn they weren't the center of the universe. Hey, look, not only does the universe not revolve around you toots, but there are probably trillions more planets in the universe just like ours. Believe it or not, we've already found a couple three of these so-called exoplanets. The field of exoplanet discovery is younger than most millennials and has burgeoned into a hot, new, exciting arena of astronomy. Sorry, I had something in my throat there. The field of exoplanet discovery is younger than most millennials and has burgeoned into a hot, new, exciting arena of astronomy since the first discovery of an exoplanet in 1992. Since then, scientists have discovered over 4,000 exoplanets in our neighborhood of the Milky Way alone. But how do we even find these planets? You gotta squint really hard. Okay, no, not really. The answer rests mostly in the physics of the stars that host these exoplanets. Now, let's take a look at the four main exoplanet discovery methods. Method number 1. The transit method. The majority of known exoplanets were discovered with this technique, mostly through NASA Kepler and TESS missions. Kepler lasted from 2009 to 2018. Then, in 2018, the Transiting Exoplanet Survey Satellite, or TESS, was launched into space. You know, my mother-in-law is named Tess. I wish I could launch her into space. Anyway, these space telescopes revolutionized the field, discovering thousands of exoplanets, many of them Earth-like. So the telescope is pointed at a star, and its brightness is observed over time. If a planet passes in front of the host star, or transits, a teeny little dip in brightness is observed. And I'm talking real teeny, dude. Like imagine putting 100 shiny pennies on the friggin' moon, and then just covering up one. These instruments gotta be sensitive enough to detect that change. From the shape and depth of the light curve, many properties are cleverly deduced, such as the planet's radius, orbital period, and even the chemical composition of its atmosphere. Alright, method number 2, the radial velocity method. This is the second most prolific technique. Its success is owed to a number of ground-based observatories, such as the European Southern Observatory's HARPS instrument in Chile, and the Keck Observatory in Hawaii. So with this one, once again, the telescope is pointed at a star, a spectrograph splits up the light into its component colors, like with the Pink Floyd prism, you know? Then the stellar spectrum is recorded over time. Now, if a planet is orbiting that star, what are you going to see? Is a periodic red shift and a blue shift as the star wobbles this way and that way due to the gravitational pull of the planet. Using this fancy equation derived from Kepler's laws, some pretty clever folks can deduce the planet's minimum mass and orbital period. And check this out. If you're lucky enough to constrain the radius from transit data and the mass from radial velocity data on the same system, you can estimate the planet's bulk density and figure out what it's made of. You know, is it rocky, gassy, cheesy, or whatever? Method number 3, direct imaging. Basically, you take a picture of the planet. Okay, next slide, please. Oh, wait, go back. I forgot a couple things. It turns out that stars are like way brighter than planets. So the trick with this one is to minimize the host star's light and maximize the light emitted and reflected from the planet. This can be done using a coronagraph, a little doohickey in the telescope that blocks the starlight, or with clever data reduction techniques, or someday, maybe even a giant robotic flower thingy NASA calls the starshade. Last but not least, method number 4, gravitational microlensing. In 1919, Sir Arthur Eddington experimentally confirmed the prediction that gravity bends light rays, famously made by Einstein. Ramstein? Einstein. This phenomenon can be exploited to deduce the presence of a planet. As the light rays from a distant star bend around a closer star and fall into a telescope on Earth, they focus and amplify the distant star's signals like a lens. If a planet orbiting the lensing star gets in the way, it further amplifies the signal, and bada bing, bada boom, you can see a little planet up to thousands of light years away. Look, pal, you can't make this stuff up, right? It's like the universe is wearing glasses. Alright, big deal. So now you know the 4 main exoplanet discovery techniques. So what? Well, in the 16th century, the Copernican theory marked a revolution in the way humans see their place in the universe. Now, the Copernican Principle has never been more salient, with increasingly more exoplanets being discovered each year. With the advent of the next generation of space telescopes like the James Webb, LUVOIR, and HabEx, it is likely only a matter of time until signs of life are detected on any of the potentially billions of habitable planets in our galaxy. How will the discovery of life change the way we think about our place in the universe? If you like this video, click this button and that button and all the buttons and subscribe and stuff. And if you didn't like this video, well, honestly, I get it. My voice is, it's not for everybody.